You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you. Hello, this is Richard Jacobs with the Future Tech Podcast. I have Dr. Paolo Ferri. He's working on the Comet mission Rosetta. He's the head of ESA's Missions Operations Department, ESA being the European Space Agency. So, Paolo, thank you for coming. How are you doing?
I'm fine, thank you. Thanks for calling me.
Yeah, tell me about the Comet mission Rosetta. What's the purpose of the mission?
Well, this was a historical mission. I say was because it's finished at the end of 2016. But it's a mission that flew 12 years in space. It took 3 decades end to end from the first idea to the conclusion. And it chased the comet, reached the comet. For the first time, it did a rendezvous with the comet, which means in space terminology means that it stayed in the proximity of the comet for more than 2 years, and even dropped a small lander on the surface of the comet. This was the first time that this was done, and it was really a fantastic experience.
Yeah, that's amazing. How fast was the comet going, and where was it going?
Well, the comet is traveling very fast. Depends on whether it's close to the sun or far away from the sun. But typically, you talk about speeds between 30 and 40 kilometers per second. It's quite a speed. The orbit of the comet is going between more or less the orbit of the Earth and the orbit of Jupiter, and it takes 6.5 years to go around the sun. So it comes back basically to the same position every 6.5 years.
But did the spacecraft that was going to dock with it, did it have to move at the same speed, or was it able to intercept it for a long enough time so it didn't have to move that fast?
It did. In fact, this is why a rendezvous is so difficult. In order to rendezvous with an object in space, you have to achieve the same speed. And there is no rocket on ground that can accelerate a spacecraft to the speed of a comet, at least not today. So what we had to do, we launched it, and then we had to encounter 3 times the Earth and once Mars, get very close to them, and get pulled by the acceleration, by the gravitational acceleration of the planet, and then pushed away, so that basically like a slingshot, the gravity of the planet could accelerate our spacecraft. So we got faster and faster every time we were getting closer to the planet. And this is why it took 10 years. We had to go 5 times around the sun, and each time encountering a different planet. At the end, we were fast enough to reach the comet. And then we were faster, in fact, because we were chasing it. So we had to slow down, and there we used our own, the small rockets we had on board to slow down the speed. And then finally, we had the right speed of the comet. But this is what makes it difficult, what makes it very long as a trip, 10 years trip. And that's why it's been done only once for now.
So it took 10 years to get up to speed and then
yes.
Get near the comet? Wow.
Yeah, it was a trip of 7 billion kilometers. So quite some time and quite some distance.
How difficult was the math to figure out that this would work and to get the calculations right to get near the comet?
Yeah, let's say the difficulty of the problem, you can divide it in 2 parts. One was the planning of the mission. This is what we call mission analysis or mission design. Practically, you have to use a lot of mathematics and computing power, because you have to plan the trajectory so that the spacecraft flying in space, encounters the planets at the right moment, four times, three times the Earth, once the Mars. So keeps going around in circle around the sun and meets the planets to get the acceleration at the right time. And then, of course, after the last acceleration, it reaches the comet while in the point where the comet is actually passing. So this is quite complicated, but it wasn't the most difficult part of the mission. This is done for most of the interplanetary missions. This technique to use the planets to accelerate, it's been done many times, and it's not easy. But once you have designed your mission, you know that this is going to work. The difficulty, and very special for Rosetta, was that when we arrived at the comet, we didn't know uh, anything of this object because a comet is hidden by its own emission of gas and dust. So from Earth, when you observe it from a telescope, with a telescope, you don't see the nucleus of the comet, the little object that eventually we wanted to orbit. When I say little, it's little in astronomical terms. It's actually as big as a mountain. In the case of Rosetta, this comet was 4 kilometers wide. In astronomical terms, it's nothing. It's really very small. It's like a dust grain. You don't see it from Earth. So we started seeing it only when we arrived, 10 years later. In fact, just 2 weeks before, 3 weeks before arrival, we saw the nucleus, which was larger than a pixel in our pictures. Then, when we arrived there, we had to mathematically describe it. So, make a model, like an engineering model of the comet with all the gas around it, the rotation, the surface, because all these characteristics were affecting the flight of our spacecraft. So this was the difficult thing. This was done for the first time by Rosetta, and we had to learn to fly around the comet while we were flying it. So this was really the challenging part, and there was a lot of math involved in that.
This is an amazing mission. When was the first time that you were able to start photographing the comet up close? And how close is up close?
Yeah, we arrived mid-July 2014. So we launched in March 2004, and about 10 and a half years later, mid-July 2014, we arrived at a distance of 12,000 kilometers from the comet. And after a trip of 7 billion kilometers, you can imagine that 12,000 kilometers was just around the corner. That's where we started not making pictures of the nucleus. We saw it before, but the nucleus was more than a dot in our picture. It was a bit bigger. We started to see the shape. Then we approached it very slowly, and by the 6th of August, so 3 weeks later, we arrived at the distance of 100 kilometers. So at this point, we stopped at that distance. Of course, we didn't stop. We kept flying very fast, like the comet, but keeping a distance of 100 kilometers. And that's where we started photographing in more detail, then started to go closer to sense its gravity. Its gravity was, of course, very faint. You can imagine the gravity of a piece of a mountain. In fact, just to compare it, something that weighs 100 kilo on ground, like our landing probe, Philae, on the comet weighs only 1 gram. Yeah, so that's the type of gravity you have there. So we sensed it, and then gradually we developed our models, and we could fly around it down to a few kilometers.
How did you land on it if things weighed so little?
Well, in fact, the gravity was strong enough to very gently pull our lander. So our landing was simply like throwing a stone towards the comet with the right speed. So with enough speed to reach the surface without being accelerated too much, because we didn't want the lander to bounce back into space. Yeah, with such a low gravity, the problem was not really to reach the surface, but was to avoid that you bounce back. Yeah. We dropped it because it was like dropping from an altitude of 22 kilometers. And it took 7 hours to fall. Very gently, very slowly, it fell towards the surface. When it touched the surface, the Philae was designed, Philae was the name of the landing module, was designed to shoot harpoons through the surface so that it could anchor itself to the surface. Unfortunately, these harpoons didn't work, but fortunately, our touchdown speed was low enough. We had done a proper job, so it bounced a couple of times, but it didn't bounce back in space. Eventually, stopped, and it could conduct its scientific experiments for 3 days.
Did it move around the comet, or had it just stay in one spot?
Yeah, no, it could not. It had 3 feet. It had the harpoons. Ideally, it should have anchored itself, but eventually it rested in that position. And it had movable parts to collect samples and to analyze them. It had many scientific instruments, and it survived for about 3 days, 64 hours more or less, using a battery which big battery that it was carrying. We had hoped with the little solar cells on the surface that it would recharge a smaller battery that it had, so to allow it to operate for another couple of weeks. But fortunately, it ended up in a very dark spot, so this secondary phase did not work. But it was good enough to perform 90% of its science. This was fine. And the majority of the scientific measurements of Rosetta were actually performed by the orbiter, by the mother ship that remained in orbit for 2 years. This was the main purpose of the mission. But then we could correlate the measurements from the orbit with the measurements on the surface. So this was really um, an amazing experience.
Was the comet tumbling or turning or rotating very much? I mean, did that disturb make it harder to land on it?
Yes, it did, of course, rotate. Practically nothing in the solar system stands still. It rotates on its own axis. Basically, the period of rotation was 12 hours, so a full revolution in 12 hours. Now, this didn't make it particularly difficult to land. In fact, we knew the period of rotation. This was one of the few things we knew before arriving there, because you can see with the telescope, you can measure the oscillations in the light that it reflects from the sun. So that was one of the few parameters we knew pretty accurately. What made it difficult was the totally irregular shape of the comet. If you if you look at our web page and you access the pictures of the comet, there are thousands of pictures. You see that it's actually composed of two objects. It's two objects. One is a larger one and one is a smaller one, which probably collided and melted together, yeah, millions or probably billions of years ago. And this made the shape not a nice and round, say, potato shape as we would have expected, but they made the shape extremely irregular. So the mathematical model, for example, of the gravity field became extremely complex to develop, yeah, because of this irregular shape. Eventually, we could do it, but it took several weeks to refine it.
So what else did you notice about the comet that was unexpected? When you landed on it, or when you got close enough to measure it?
Yes, okay. Well, I can speak for the scientists because, in fact, I am not working on the scientific part of it. The scientists are, if you want, my job is to bring the instruments of the scientists to the target, to the comet, and to bring back the data. Then they do the analysis. But I can quote many surprises that these people got. For example, a very important result, although it was a negative one, they analyzed the isotopical composition of the water. So basically, how much was the ratio between normal water and heavy water in the water that is emitted by the comet? And they concluded that this has nothing to do with the water we have on Earth. This sort of killed all the theories, or at least put in doubt the theories that comets have brought water to the surface on Earth. If this has happened, it was definitely not comets like the one we have analyzed. So all this theory has to be reviewed now. Another big surprise was how hard the surface of the comet was extremely hard, while definitely the inside is much softer, because the overall density of the nucleus is less than half of the density of water. So it's a very light object. You can imagine this is a mountain, so it weighs 10 billion tons. So it's not that light. But if you throw it in an ocean, it will float almost completely because it weighs less than half of water. So it's inside. There's a it's now basically demonstrated by Rosetta because we did also some tomography of the nucleus. So we used radio waves to see what's inside. And inside the comet has a very high porosity. So it's basically made of material, but with a lot of air in it. So this was a big surprise.
So interesting. You said the comet's always throwing off dust and water vapor. I'm looking at the pictures of it, but it just looks like blackness is around it, the blackness of space. But could you see things volatilizing off the surface or being thrown off the surface? And did that create a wind or anything that disturbed the lander?
Yes, definitely you can call it wind. Of course, it was very light in terms of force impacted on the spacecraft, but we had to model that. This was part of the difficulty. Before getting close to it, we had to get a sort of measurement of how strong this wind was. And of course, the wind was different depending on the part of the surface we were flying over, because the comet doesn't emit gas and dust uniformly on its surface. It has really some hot spots where, like geysers, you can imagine, that they are stronger in emissions. Sometimes there are even explosive emissions, because the sun hits the water under the very hard crust, and then when the pressure inside is built up, the water breaks this crust and explodes into the surrounding. So let's say overall the pressure on the spacecraft was not very high, but we had to model it. And then, of course, we had to avoid these explosions, which would occur relatively unexpectedly. And then the big problem was the dust, because while we approached the comet when it was still far away from the sun, so it's pretty inactive. So quite let's say we had hardly any dust and gas around it in the beginning. But then we approached the sun, and it became more and more active. So we had to increase our distance from the surface. Initially, we were down to 10 kilometers, and we went up to a few hundreds of kilometers. While we were still orbiting it, still following it, but from a larger distance, because the dust around the comet was so much that we couldn't see the stars with our little telescopes on board the spacecraft. The spacecraft needs to detect the stars in order to realize to determine its attitude. So it's not its position, but the attitude with respect to the inertial space. And because of this, the dust was obscuring the sky, so we couldn't fly so close. So we had to back off a bit. We went to a few hundred kilometers. Then there was less dust, and we could keep analyzing, but from that distance.
So you got into line with the comet, started chasing it, following it as it was approaching the sun?
Correct. And in fact, even beyond the closest point to the sun, we continued following it. So basically, we arrived in August 2014. The closest point reached to the sun was in August, actually a bit earlier, I think it was around June, July 2015. And then we continued. So the comet started going away from the sun. The activity went down, and we followed it. And in fact, we could go closer again. And we finished the mission in September 2016, when the distance from the sun was so large that we would have had to switch off the spacecraft anyway. So in these last few months, we flew closer and closer down to 2 kilometers from the surface, and eventually in the last day we gradually landed, so gracefully landed Rosetta, the mother ship, which was not designed to land. We landed it on the surface, and then we programmed it such that once it touched down the surface, it would switch off itself. And now it rests on the comet forever.
Really?
Yes.
You don't think the comet would slough off the comet and fall into space at some point?
Okay, this you cannot exclude. Yeah, of course, comets evolve a lot when they come closer to the sun. It could even be that the two pieces that melt in the past will break off one day. We've seen big cracks on the on the neck that links these two pieces. In fact, if you look at the shape of the comet, it resembles a bit of a rubber duck, and so we tend to call the smaller lobe the head and the bigger lobe the body. And in the neck, in between, we've seen signs that most likely in the future, maybe tomorrow, maybe in 100 years, the two pieces will break off. So we have seen the surface of the comet changes dramatically from before to after a passage close to the sun. And since this happens every 6.5 years, I don't know what's going to happen to Rosetta. It could be that it gets spit off of the surface, but then the gravity will probably attract it again. I don't know. I don't think we will ever know unless somebody goes back and visits this comet in the future.
So you don't think that landing the spaceship on it will alter its trajectory? I mean, if it splits, it certainly definitely will alter the trajectory, yeah. But that's not caused by this.
Yes. But no, not certainly. Again, we're talking about an object of about 1.5 tons. This was Rosetta, hitting very gently an object of 10 billion tons. So, no, there's no change in the orbit, I can guarantee.
What else did you learn from the comets? I mean, anything about its structure or its origin, or the water on it was somehow different? I mean, what are some details?
Yes. So, okay, the difference in the type of water was, as I said, very, very important, because we expected exactly the opposite. We thought that we could confirm that water comes from comets. It didn't. There's been many discoveries because we could analyze both from the orbit and from the lander. We could analyze really a lot of the material on the comet, because the comet spits it to you. It's a big advantage of flying around the comet compared to a planet. So, for example, Rosetta discovered very complex organic molecules down to parts of amino acids. And this was not completely unexpected, but because there were many theories predicting that, but it was an important confirmation, because comets are extremely old. They are probably the oldest things in the solar system that were preserved in their original composition and structure, because they existed before the planets and the sun formed. It was sort of proto-planetary nebula. So there was this sort of big cloud of dust, and comets are part of this. It collapsed 4.5 billion years ago, collapsed in the center, the sun ignited, then the planets gradually attracted all the dust, or most of the dust, and this dust was compressed, high pressure, the gravity, and so on, so it was more fully modified, and they swept away the rests, the remaining parts, which are the comets, to the periphery of the solar system. So one can say the comets are what was left over from the formation of the solar system. They are very ancient. And if on these very ancient objects you can find already extremely complex organic molecules, you can sort of assume that the process for the formation of life on Earth did not start from zero. It started from already something very complex. In fact, there are indirect proofs of life on Earth already back to, I think, more than 3 billion years. Well, what happened, of course, for the formation of life, we don't know. But we know that already complex components existed from the beginning.
Were you able to take any samples and bring them back, or it wasn't feasible to do that?
No. In fact, when it was conceived in the beginning, I'm talking about mid-80s, Rosetta was thought to be, well, at that time it was not even called Rosetta, it was called Comet Sample Return Mission. And the idea was to bring back samples to Earth. This idea was discarded relatively early, just a couple of years after the initial discussions, for two reasons. One was the complexity of the mission. The risk would have increased dramatically at that time. At that time, basically nobody had even attempted a rendezvous with a comet. Imagine getting there, landing, collecting a sample, bringing it back. So this was one reason, very high risk for the technology we had at that time. We're talking about the late 80s. The second reason was that if you want to bring back a sample, you need to you basically to dedicate most of the weight of the spacecraft to the tools and the systems that you need, the capsule to bring it back, and the tool to just dig it out and put it back in the capsule. So you waste all this mass to bring back a small sample, while with the mission of Rosetta, we used all this mass to bring a large number of scientific instruments to the comet. So basically, instead of taking a small sample, bringing it back and analyzing it on Earth, it was considered scientifically more opportune to bring a lot of instrumentation from Earth to the comet, do the analysis locally, and bring back the data. So eventually, we are convinced that the mission of Rosetta, the way it was eventually executed, scientifically obtained much more than a sample return would have obtained. It doesn't mean that in the future we wouldn't like to try a sample return. For example, NASA has in one of the future missions a proposal not yet approved to actually go back to the Rosetta comet. The comet is called 67P Churyumov-Gerasimenko, is a pretty complex name. Go back to the comet that Rosetta has analyzed and described and characterized. Being a second mission, the orbiting and characterization phase becomes much easier, of course, because Rosetta has done all the precursor work, but then concentrate on bringing back a sample to Earth. So there are already studies to do that. One day probably a sample will be brought back. Yeah.
Was the comet composed of anything interesting, or was it just the same minerals and things that we see on Earth, just arranged a little bit differently?
Yes, certainly no unknown materials that we could identify. There were some surprises. For example, there were molecular versions of noble gases, molecular versions of nitrogen. It was for the scientists surprising to find them there, because it was thought in the theories of the formation of the solar system that these gases in molecular form would actually form much later during the process of the formation of the planets. And to find them there in this very ancient object was unexpected. So the scientists actually had to throw away a lot of theories about the formation of the solar system. They are now busy analyzing the data to see whether they can update these theories, and so that they match the data that Rosetta and the observations of Rosetta. So no new material, but certainly complex material like the organic material. That was a bit surprising to find it in such an ancient object.
What do you feel like were the most useful things learned from Rosetta? Is this one of them? Are there other great learnings that you like?
Well, I always say, when people ask me why we do missions like Rosetta, I always say that the science is, of course, the official reason, but it's not the only outcome. So all these scientific results that I'm quoting, again, it's very difficult to say which one is the most important, because altogether they contribute to update our theories about comets and about the formation of the solar system. But science is one aspect. There is the second aspect, which is the technology and the expertise. I mean, thanks to the Rosetta mission, there is now know-how, which didn't exist before, on reaching a comet, orbiting a small body like a comet or like an asteroid, and landing on it. These are all techniques which will become extremely important in the future. Of course, we've done it only once, and we've learned from various things that we did right and we did wrong. But it's going on this route that one day we will be in a position, for example, to define, to do things like some people are already dreaming of, which is doing mining on asteroids, and reaching an asteroid, landing on it, and start extracting material to bring back, say, precious metals or so, or to bring back to Earth. This is one commercial aspect. Another important aspect is, comets and asteroids are a potential danger for the Earth. They have hit Earth in the past. They've even most likely killed the dinosaurs. They've really affected the evolution of life on Earth. And they will hit Earth in the future if we don't do anything. So developing technologies, well, knowing what a comet is made of, knowing its internal structure, its surface, and developing technologies to land on it could help us in the future to define missions that one day could be sent to a threatening asteroid and, for example, deflect its trajectory so that it doesn't hit the Earth. If I may, there is a third aspect which I always consider extremely important. Missions like this become really a pusher for young generations to be inspired, to do science, to study, all these scientific, mathematics, or engineering disciplines. They get this type of push from the emotions of missions like this. I can say it on myself. I was 9 years old when they landed on the moon, and this event, although I was such a young kid, certainly determined my aspirations and eventually my future career. And I've seen the effect of Rosetta, missions like Rosetta on small kids, and this is, for me, also an important outcome of a mission like this.
That's great. Well, Paolo, what's the best way for people to see pictures of the Comet Rosetta and the mission and to find out more?
Well, the best that I always recommend, of course, if you go on the European Space Agency website, you find a lot of information about Rosetta and also about the other missions that we're flying from here. I always recommend to access the Rosetta blog. This blog was activated just in the last 2 years, and it was updated basically on a daily basis. And it has links to all the possible information from science, from the pictures, from the technology. It has anecdotes from our operational work, which was really every day exciting and every day new. If you type in a search machine ESA Rosetta blog, you find the link. I'm still learning from it. If I have the time and go back to it, I learn more and more things. So I think that people would really like it.
Well, that's great. Well, Paolo, thank you so much for coming. I appreciate it.
You're welcome.
You're listening to the Future Tech Podcast with Richard Jacobs. Future technologies such as artificial intelligence, stem cells, 3D printing, gene editing, Bitcoin, blockchain, the microbiome, quantum computing, virtual reality, and exploring space are much closer than you might think. In fact, many early versions of these technologies are in play right now, and the companies that are using these technologies are the focus of this podcast. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a thorny medical problem. Remember, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you've enjoyed the podcast, please listen, subscribe, like, and tell your friends about it. Thank you.